morning. So it's period number 4, last period of this academic year. So we have a 7 more weeks to go. And what's going to happen in this period that I will explain you momentarily. But what I would like to do in today's lecture is that I kind of like to still go back to these flexible multi-body dynamics and look at the two things that I would like to explain to you. And those two things that I would like to explain to you are how to do this mode selection. So we know how to compute these assumed deformation modes. So we know that we can do that by using an eigenvalue analysis, or if we want to be more advanced, then we can use the Craig-Pompton approach. But still, we haven't really discussed about what next. So if we can have set of modes, which out of these many modes are the ones that are most useful for us? And these mode selection techniques, and what are the procedures to make good calls about how to select the proper modes that I would like to share with you today. And then a minor detail, kind of like a theoretical detail, which is related to how to actually you can combine description of flexibility and multi-body system dynamics that I would like to discuss after that. And that's called mass invariance. Mass invariance is a highly theoretical subject matter. Oh, I can see that my camera is frozen already. Um, Maybe that was the reason that this bitrate complaints came. Maybe. So let me refresh my camera. Still not refreshed. Okay. Okay, so let me see where are my other cables because I have another camera here. Oh, I think now it's gonna be okay. All right. So yeah, I was about to explain about this mass invariance. And the mass invariance is something that is theoretically very challenging. So it's a big mess. I need to warn you. But it plays a significant practical role. And the significant practical role is the fact that the mass invariance is the way to combine description of flexibility and multi-body system dynamics. So it's like how tightly you combining your finite element model to your multi-body system dynamics. And that surprisingly, there are many variants, I mean, many options to do so. And how that can be accomplished in a practical case, that is explained by mass invariance. And that's about it. And then right after that, we are not going to discuss about any more about the flexible multi-body dynamics. So we're gonna close here discussions about the flexible multi-body dynamics, and we're gonna move on to completely new topics. And we get started from the contact modeling. And then there's gonna be a wide variety of other kind of like mixture of different topics. And the contact is the first thing to discuss. Look at this. So why is that my camera seems to be all the time frozen? So I guess that it would be better to use another camera. So just a second. I need to do a little bit of need to change my settings a little bit. Here is another cable. Like this. Okay. Yeah, look at it seems that my current camera is not willing to cooperate at all. So let me just change it to be another camera. Hmm. Okay. All right, so here it is. This is a camera that is not so great quality than the previous one, but that seems to work okay. Okay, so the content modeling will be right after description of flexible multibody dynamics. Oh yeah, and let's first get started from the practical matters. Let me take myself to the back to the presentation. So here it is. So the first thing that I wasn't really sure about is that how is that we can do face-to-face teaching. I was actually this morning I started to look at the instructions and I recognized that there was a email from rector saying that starting from today, starting from this Monday, university goes back to the face-to-face teaching. But it was kind of, if I remember correctly, it was mentioned such that we can go to face-to-face teaching by steps. I don't know what are those steps are and how is that we should do that teaching. Now this is something that I need to figure it out. But you see that already this lecture is going to be online lecture, one more online lecture. But I'm thinking, this is what I'm not 100% sure, but I'm thinking that starting from next week, Monday, we will get these face-to-face discussions. And how this course will continue from this Monday on is we're going to have a number of visiting lecturers. And the first visiting lecture will be delivered by Professor Arend Swap. Arend is a professor in Delft University. And you know that the Delft University is very high ranked university. So it's one of the best universities, technical universities, particularly in Europe. And Arend's going to explain a little bit about how is a vehicle modeling, and he's going to focus quite a bit about the bicycle dynamics, but there's going to be more discussion about the vehicle dynamics as well. So not just two-wheel vehicles, but other vehicles as well. Then what follows week after that is a PLM lecture that will be delivered by Dr. Ilkka Nonokwe. And that's going to be something that is giving you a little bit of different kind of point of view. So this tells you how is it you can link your simulation to other kind of like software products that are very often used in companies. Particularly if you go to one of these major size companies, you need to be aware how is it you can link your work to other people's work. And that's Ilkka's lecture is going to be about or explaining you how that can be handled. Then there's going to be one more visiting lecture or maybe two more visiting lectures. The next one will be delivered by Dr. Adam Klodowski, and it's about the biomechanics. Biomechanical simulation, and it's a biomechanics can be considered as one of the application of multibody system dynamics or one of the application of dynamic analysis, as is the case of vehicle dynamics as well, particularly bicycle dynamics. And so there's going to be two applications, vehicle dynamics and biomechanics. And then the BLM, that's going to be more like for your information, more like business perspective, which too is important to know. And how is it you can link your work to other people's work when you're working in industrial companies. And then beginning of April, hopefully there is going to be one more listed visiting lecture, which is about finite element modeling. What are the recent trends and recent developments associated to finite element modeling? And in that, I'm hoping to offer you a little bit of insight about how is a multi-physics simulation that can be conducted using a finite element modeling. This is something that is very much in a fashion, and how you can do that in practical cases. I hope that there will be somebody as a visiting lecturer to explain that to you. If not, then I will do it by myself. Then there's going to be one or two more lectures to go. Future of simulation or future of computer aided analysis, put it in a bigger perspective. I will deliver that to you in April 11th. And then there's going to be an Eastern break. and then maybe one more lecture, depending how fast we can proceed in these other subject matters. So this is what's going to happen. And then there's going to be again one more midterm exam, and then you need to submit your simulation assignment, and then you're done. Then you're done. Okay, so that's the plan now. But I think it's going to be a lot of fun for you. I particularly enjoy this Orange Swap lecture. He's a very, very talented lecturer. And if you Google his website, you will recognize that he's been delivering lectures even to TEDx. And the TEDx, you need to be a good lecturer to make your way to that. And then Ilkka is also very good. Adam, I'm enjoying his lectures all the time. So I think there's going to be a lot of fun. All right, so that's what follows. Like I say, I need to figure out the instructions, but I'm thinking next week, Monday at 8:15, we are not going to have these uh, online lecture, but instead there's going to be a lecture, face-to-face lecture delivered physically in one of the lecture rooms, which I don't remember the number anymore. But those of you that are unable to come to Lappeenranta, that's okay because we're going to stream out that lecture anyways. And it's going to be the same YouTube channel than any other lecture, so no worries. No worries. Okay. And also, finally, it will be nice to have like real interaction, not just through these in-class quizzes, but the real interaction. Like you guys can argue and you know play some serious questions about what about this and that. You can have some doubts and so on and so forth. And all that is so much more easier to do once you are sitting with me in a lecture room. So I'm looking forward to see that to happen. Hopefully it will happen. But again, like I say, I will figure out the rules. All right, so here is what we need to discuss today. So those are all about the practical matters, and another piece of practical matters which I'm sure you would like to learn is that when is going to be the grading ready for concerning your first midterm exam. Answer is that I don't know. I need to find a little bit of time to look at those answers, but I'm hoping that it's going to be not taking too much time. Not taking too much time. I'm kind of hoping that sometimes not, if not this week, then week after that at latest. Okay. Um, right. So now with that mode selection technique. And now before we can move to mode selection technique, let me shortly refresh your mind about how are the ways that we can select or we can create those modes. Like I said in the very beginning, the most common way, well, let's say that was an incorrect statement. So let's just say the one way to do these modes or produce these modes is using an eigenvalue analysis. The problem with eigenvalue analysis is that you either have to set your reference condition, which is that how you're describing your motion in multi-body system dynamics in such the way that there is no boundary condition in your finite element model. Meaning that if you're dealing with the beam-like model, so you put your beam-like, not the model, but the beam-like structure. If you deal with the beam-like structure, you kind of put your beam-like structure to space, and then you conducting the eigenvalue analysis. And then you get these modes that are these free modes. So the first one will be something like banana mode, like this. Second will be more complicated like this, and so on and so forth. So you get a lot of modes. So this is one way to create it. You could also introduce some boundary condition to your finite element model. So it could be simply supported boundary condition or something else. But which one is the correct boundary condition? That's sometimes it's a little hard to define, and particularly when you wanted to describe something locally, it becomes to be very, very challenging to do so. So that's why there was this other alternatives. Instead of using just a pure modes that are coming from the eigenvalue analysis, you could also use the modes that are based on the Craig-Bampton method. And Craig-Bampton method is something that is made for general cases. So it's kind of like the approach that should work no matter what's the problem you're looking at. The idea of this Craig-Bunter method is that you divide your finite term model to two different, or let me rephrase it. So you divide your not a degrees of freedom in your finite term model to two different categories. The one that is called boundary degrees of freedom, and then other ones are what is left away from the boundary degrees of freedom are considered as interior degrees of freedom. All right. So that's the selection what you need to do. And actually what you need to do is that you just simply need to select what are the boundary degrees of freedom. So what you're going to do with those boundary degrees of freedom is that you will get some local information concerning that particular location of your structure. And now using this kind of approach, you can get the modes that are easily applied to any kind of practical problem you're facing. So it helps you to describe local deformation, which is very difficult when using these modes based on pure eigenvalue problem. And and that's about it. And how it goes in theory-wise, we look at this shortly, just prior to midterm exam. And we concluded it goes such the way that you first do this selection. You're selecting or you're categorizing your nodal degrees of freedom to boundary degrees of freedom and interior degrees of freedom. And then you're reorganizing your stiffness and mass according to that selection. And once you do this reorganization, this is how your equation of motion look like. All right, so it's representing this structure here. What you're going to do next is that you're conducting an eigenvalue analysis, but not the one that I was explaining earlier, but the one that you just take a look at the interior degrees of freedom. So you're kind of fixing, well, not kind of, but you do fixing all the boundary degrees of freedom, and you look how the structure behaves otherwise. And then you're going to get the modes that are representing eigenvalues and eigenfrequencies associated with the situation where these boundary degrees of freedom are fixed. So let's take a look. So if you have a beam-like structure, you're selecting this point here and this point here to be those boundary degrees of freedom. Then your modes will look something that this is fixed in a crown, this is fixed in a crown, and then the modes will be something like this. Sorry that the low quality drawing, but you get the point. If you have here one more boundary degrees of freedom, you're attaching this one too to crown. So then your mode will be something like, let me change my color, something like this. I'm sorry that this is a low quality drawing, but you got the point. You got the point. So there's no displacement in this point, no displacement in this point, and no displacement in this point. But other points, they do have some unzero, displacement other than zero. Okay, so this is how you do that mathematically. All right. So you're conducting that, and then you're going to combine that with another set of modes. Another set of modes is the fact that, or it can be accomplished in a way that you introduce a unit displacement to these boundary degrees of freedom one at a time. All right. So if we again have this beam-like structure, this is my boundary degrees of freedom. This is my boundary degrees of freedom. The unit displacement could be like here. The deformation would be something like this. It could be this direction here, this rotation as well. So we've got the sort of good number of different kind of modes that are based on the unit displacement. And then you will do that same for this end here. So it will be displacement like this. There will be displacement like this. There will be rotation like that. And you will get the modes that are considered to be a static correction mode. Correction mode, because they're correcting these first set of mode. What you can then do is that you can combine these two modes. Now here are the proper names. That the first set of modes is called fixed interface normal modes. What a monster name, but that's how they are. And then there's this static modes. And what you can do is that you can stop here. But you could also continue one more step ahead, and you can force these static correction modes to be orthogonal, because initially they're not. They are not orthogonal because the displacement in general is not capable to introduce orthogonal modes. Remember the orthogonality, or the definition of orthogonality is that the modes are independent with respect to each other. That's going to be hard to do if you have displacement. In general case, you cannot get the orthogonal mode when you're introducing unit displacement. This is a pure mistake. I would consider that like that. But you can get rid of that by comparing the new mass and new stiffness based on this combination of, I need to take a look at the names again, fixed interface normal modes and that static correction modes. And then you get the new mass and stiffness. And using the new mass and stiffness, you can conduct an eigenvalue analysis again. And this new eigenvalue analysis is called as or the normalization procedure. And now you can get the modes that are kind of roughly free modes and something that is called static correction modes. So here it goes. So you get these fixed interface normal modes, static correction modes. You conduct these eigenvalue analysis again, which is called orthonormalization. Why this is called orthonormalization? Because what you're essentially doing here, is that you're forcing the static correction modes to be orthogonal. That's what you do. And then you get these roughly free modes and roughly boundary modes, and that's it. Then you're good to go. But now my question to you, and I don't know if how hard it is for you after a 1 week break, and how much you can actually follow me, but I have my first in-class quiz to you. And my first in-class quiz is this. Grid-bound method is often used approach because. Then I have here 4 options. One of them is correct. And the first one is that it allows to describe local deformation due to the forces and joints. That's why it's often used. The second option is that it can be used for beam-like structures. That's what makes it famous. And the third one is that it can be used for plate-like structures, and that's what makes it famous. And the final one is that it allows to describe structural damping, and that's why it is very popular. Now, which one is the correct one? And I got first answer in my in-class quiz. And I see that I have 12 viewers, which I think it is roughly the same amount of viewers that in just before the midterm exam. So which is good news because I see that you are not giving up because of the midterm exam. I mean, you shouldn't. You shouldn't because you recognize that the midterm exam was easy. Second midterm exam, if possible, is even easier than the first one. So it's going to be basically asking like how you like the weather, what is your name, stuff like that. Then a little bit about, what about the vehicle dynamics? What are the things that are important in the vehicle dynamics, in biomechanics, and so on and so forth. But still, roughly speaking, is not going to be difficult at all. So you're just following these lectures and particular visiting lectures, and you will be okay. And I see that I have 4 answers in my in-class quiz, and still expecting a couple more to come. All right. So let me switch to this one. Okay. So you see the number is growing, so it's still 5. So it's kind of low, a little bit low. Okay. And then finally, I'm able to explain about how is this selection process then. So just a second, I'm just taking a look at the slides that I'm about to show to you. Okay. This mass invariance, by the way, is something that I will be fast. I'm not planning to spend too much time for that. I got 11 answers. When I look at the number of viewers, it's 12. So I guess that's it. And the game is on. So game is on. So I get the first vote regarding the success rate. That's the first voting is 100%. So we'll see. We'll see. My personal voting is not 100%, but it's going to be something like 90. That's what I'm voting. What about others? I got 15 viewers now. So can you please play with me? I guess not. Ah, okay. By the way, now I just the person just voted. I would like to thank you, that person, because I got your email about the typing mistake you were able to find out in my notes, and I appreciate them a lot. And and it amazes me that how accurate you are, because usually people are not looking at the derivation too carefully, and that's something that I definitely appreciate. Okay, now we got 12 answers, and I guess that's it today. So there's not more people following this lecture than just the 12 people. So the result is this. What? So we're scoring very, very low. So it's 67%. 67%. This is a unusually low uh, success rate. So let me go back to this one. Hold on. No, I want to. So what happened to this? There, this one. Finally. Okay. So the method is very often used because it allows to describe this local deformation, and the local deformation doesn't really matter where they're coming from, but the most usual suspects are forces and joints, because not much other things can cause a serious local deformation except the forces and joints. Forces and constraint. Constraint too can be considered as a forces. So it's like two different kind of forces that can introduce this local deformation. Yes, it can be used for beam-like structures, but that's not what makes it famous. Yes, it can be used for plate-like structures. That is correct too, but it's not a unique feature of the method, and it allows to describe the structural damping. That too, but it's not a unique feature of this method. The unique feature is the fact that it allows to describe a local deformation. All right. Now, going back to these finite element types. Those of you that are familiar with the finite element method itself, you know that there's a lot of different element types available. Many, one of the most often used are solid and plates elements, beams perhaps. And what I have recognized so far that due to the computational power, most of the models at the moment are based on solid elements. These structural elements, which is designed for certain kind of structures like beam-like structures, say cell-like structures, plate-like structures, they're not so frequently used at the moment. And I've been explaining that to myself, that this is simply because of the available computational power. Because if there is enough computational power available, you don't need to think too seriously. You just measure your structure by using solid elements, and it works out for any cases. But the problem could be that if you have a plate-like structure, let's say that you have a thin plate like this. Let's say that this is 1 meter this direction, 1 meter this direction, so 1 meter, 1 meter, and then this is a 1 centimeter thick. So let's say that it's 0.01 meter thick. And now to model this by using solid elements, you need to use quite a bit of solid elements because you cannot distort the shape of the solid. I mean that you can, but when you do so, you're usually losing quite a bit of computational accuracy. So you are not getting accurate results anymore. So you cannot model this by using a solid elements that are, 1 centimeter thick like this. And then they are like, let's say, half a meter this direction, another half a meter this direction. You cannot distort your solid elements like this. The only way to model this by using a few number of elements would be using plate-like structures. I mean plate elements, which is designed for plate-like structure like this. Obviously is a plate-like structure. And then this will be the most computationally most efficient way to do that. But anyways, like I said earlier, I recognize that most of the models at the moment are based on solid models because no thinking really needed. You just take your cubicles, you're messing your structure by using cubicles, and that's it. Simple like that. But anyways, when you're using these modes, and when you're combining finite sum method with multi-body system dynamics, you can basically use whatever element you want. But still, the most often used are solid and plate elements. Beam structures, what mentioned here, are often so simple that you can use a lamp mass approach. That's not always the case. There's sometimes the beam structures are still complicated enough. They are kind of requires a very accurate modeling. So the beam elements could be used together with the floating frame reference formulation. So it's not necessarily always the case, but there are sometimes the cases that the beam structures are symbols, they are straight, so they are not too difficult to model. And it's easy to model then by using simply lamp mass approach. Whatever you're using modes, whatever you're using free modes or Craig-Pompton method, it's very important to take your rigid body modes away from your model. Why is that? Because remember, what we do in the floating frame reference formulation was this. So we have this reference coordinate system, which describe the motion with respect to global coordinate system. So this is global coordinate system. This is a reference coordinate system. And the reference coordinate system, this one here, is the one that is describing the rigid body motion, large reference motion to be more specific. Large reference motion is described by this coordinate system. So no modes are needed for that purposes. And actually, the modes wouldn't be able to describe that accurately. So you always need to take these rigid body modes away. How you can recognize the rigid body modes? Well, first of all, they look like motion which there is no deformation, and they're always associated with zero frequency. So that's how you can recognize the rigid body modes. So take them away. So that will be, there will be no need for rigid body modes because the rigid body motion will be described by reference coordinate system. Now the finite sum models that are conventional, that are used in the structural strength analysis, can be often used as they are. So there is no need to make any kind of modification. But there is an exception. The symmetry models, like 1/4 models or 1/2 models, they cannot be used. So those will be very, very hard to use. I don't think they are that much in the fashion anymore. But okay, so when I was in your age, the computational power was not so great. And most of the finite element models, they were these 1/4, 1/2 models to save the computational power. But I don't think that they're used that much anymore because they are not used that much anymore. So maybe not need to discuss this in details. But symmetry models, don't use them. They're not going to work out well. But my next in-class quiz is this. In the floating frame reference formulation, rigid body mode needs to be removed because rotations are assumed to be small, deformations are assumed to be small, reference coordinate system takes care of the rigid body motion, damping is assumed to be insignificant. Okay, so let's see how we're going in, how is we doing in this second in-class quiz. But this is what I just explained to you. So would you like to go back here? Just hold on, now I need to find my mouse here. So this was what I just explained to you. And now we're going back here. And we started to get the answers. Let me, this one, that's how it goes. Here is my mouse. Yeah, by the way, this face-to-face lecture about that will be delivered by Aren Swap. So Aren will arrive to Lappeenranta on Saturday. So he's ready to deliver his lecture on Monday morning. But again, I need to double check whether or not this is according to COVID rules. And we got the new voting action. So we got the first, which is 80%. Okay, so now so no one is no longer voting 100%. You guys getting to be a kind of like suspicious about your skills. You shouldn't, because remember, the most important thing for us is this can-do attitude. Okay, 6 answers. I will leave you guys to think about this, and while you think about that, and I will get back to that momentarily. All right, so here, finally the mode selection. The mode selection, and there are, like I said, there are tools to do this mode selection. Yes, there are tools, and we're going to take a look at these tools momentarily. But even though that we have those rules, the most efficient way to do this mode selection is to use not the common sense, but your engineering sense. And you need to take a look at like what is a possible deformation that could be introduced of your forces in your structure. And this is a simple case. Like if you have all the forces in plane, you have like a crane that can only move in a planar motion. So then it makes no sense, or makes a very little sense to introduce this off-plane deformation modes. You can have them one or two, but don't take more than that. And you have to understand that when you're creating those modes, the creation process itself cannot understand what's going to be the use of the modes. So it will give you like a full set of modes, and then you're the ones that are deciding whether or not you're going to use these modes or not. And the most important advice in that is to take a look at how is the deformation mode look like, and then use your engineering sense. And now this instructions is coming from Adams, which is a commercial software similar than Simscape. And in Adams, you can have this animation. So you can click each of the modes, you can animate them. Look how they are. How is the visual appearance? And now based on the visual appearance, you can make your call whether or not they are something that it makes sense you to take those into account. Also, make sure that kind of the advice which is often used, that please use this Craig-Pompton method, which is criticized a little bit in academic community, but it's still kind of often used because it allows to describe this local deformation. And this local deformation is often important, particularly if you wanted to predict the stresses and something that is used, for example, in the fatigue analysis. So it makes sense to use it. But again, you have these two set of modes, which is the free modes. This is how they look. So this is a free mode. You said that this is no boundary condition at all. Second free mode, and then this boundary mode. The boundary modes are often associated with the higher frequencies. This is another thing that you need to be careful with, because the high frequency here can lead to this numerical stiffness. Remember, the numerical stiffness could be a problem because that leads to a situation that you have low frequencies. And here's an example about the low frequency. This is a 51 hertz, this deformation mode. And then you have here deformation mode, which is what is it, 2768 hertz. So the scaling difference is huge. And now because you have these low frequency and high frequencies, your time integration scheme is struggling because of that. You can make some tricks when you're using these modes. And one of the tricks you could consider is that you can introduce the very heavy damping associated to frequencies that are high. it could be critical damping. That means that system can deform this way, but it cannot vibrate in this way. That helps in terms of how to conduct this time integration scheme. But still, this is something that is good to keep in mind, and you would like to avoid this stiff system as much as you can. All right. Now I'm going back to this one here. This is the first in-class quiz of the day. Let me switch my screen a little bit. So here it is, and we got the votes that are 90, 86, excuse me, 80, 96, 91.7. That's very accurate. 83 and 74. The winner is, oh, that's really close. No, well, there is 80 is close enough. So we got one winner. That's a good call. Now, back to this. Let me take this away. Not this one. This one. Which one out of these options are correct? Of course, is the fact that reference coordinate system takes care of the rigid body motion. Or maybe this is incorrect to say rigid body motion, because actually, academically, there is no such thing like rigid body motion. There is only large reference motion. But, in the daily life, in common sense, it means rigid body modes. Okay, so it's not about the rotations are assumed to be small, because the rotations are not assumed to be small. Deformation is assumed to be small. That is correct, but still had nothing to do with this business. And the damping, we haven't discussed that damping at all, so that's not correct solution. So the correct one is C. Now, back to this selection procedure. Here's my mouse. Now, what is then the way to do this selection automatically? What are these tools available? This again is a screenshot from Atom software. And I think this kind of option is available in all the commercial multi-body software. And this is the tool that allows you to automatically select the modes. And the automatic selection goes such the way that you are simulating your system by using all the modes that you have computed. All the modes that you have computed. Now let's see that, let's think about that you have used a Craig-Pompton method. In the Craig-Pompton method, you have computed roughly 100 interface mode and roughly, let's say, 20 static correction modes. So it's going to be a total of 120 modes. And what you're going to do then is that you're running your system using the entire work cycle of whatever system or whatever way you wanted to analyze using these all 120 modes. And then you're going to set the threshold value. And the threshold value here is considered the energy tolerance. And now if a single mode is contributing less than preset tolerance to strain energy, then it's considered to be insignificant. And it's a very simple way to take a look at that. And typically when you look at how much a single mode is contributing to energy, the strain energy, it goes such that there is like 5 modes that are contributing a lot. Let's say 90% of the contribution comes from the 5 modes. The rest is coming from the modes that are contributing maybe, let's say, 2 to 5%. And then there is a lot of modes that are contributing less than a percent. Less than a percent. It can be way more than less than a percent. And those are obviously the ones that are not making much of an effect to accuracy. So you can easily ignore that. And that's what the tolerance is standing for. So that's where that is coming from. Okay. So let me try to explain. This is another way. Strain energy can be computed in a way that you take the. No, let me rewrite this completely. Okay, the strain energy can be computed in a way that is integral over the element. So it's the strain multiplied by elastic coefficients multiplied by strain, and that's it. That's how you can compute the strain energy. Now this one here, the strain, you can break down to each one of the modes in such the way that, remember that it goes such the way that the strain can be expressed by using this B matrix. This is supposed to be B matrix, so this is a kinematic matrix multiplied by nodal displacement. Now the nodal displacement can be expressed by using this deformation mode multiplied by associated the modal degrees of freedom. Now this is for each one of the modes. So what you can do then is that you can take the mode number one and associate the modal coordinates into account, and you can see how much energy that is contributing by substituting that to this equation. And when you're summing them to up, when you're putting them all together, then you get the total strain energy of the system. And then you can see how much each of the modes are contributing to total energy. And now if the contribution is less than this number here, so I just messed the number, the error tolerance, no, energy tolerance to be more specific here, then it's automatically ignored. So it's automatically doing this selection procedure for you. So here's the good news. So you can do it automatically. The bad news is this. So if you're changing your analysis type, let's say that you're analyzing your grain and you're moving payload from here to here in your grain, you can compute it first by using your old deformation modes, and then the selection can be carried out automatically. But now if you're changing your analysis type, even so simple that you're no longer moving the payload here to here, but you're moving payload here to here, you need to redo this automatic selection. And that's a little bit annoying because typically when you do this automatic selection procedure, you just don't need to redo the simulation anymore. So it's just that, if you keep it all them together, so there's no need to reduce the modes anymore. So that's the bad news. So what is left then? What is left is your common sense. Let me correct that. Your engineering sense. That definitely is the best way to do this selection. And in your engineering sense, you take a look at how you're animating, how the deformation mode looked like, and then you think whether or not it makes sense to keep those as a part of your simulation. Okay. All right. So then, so here are the same thing that I just explained to you. So the model is first analyzing using all modes, and then the modes that are contributing insignificantly, less than the tolerance value, this is a tolerance value again, are automatically eliminated. And then you can use a reduced set of modes. So that's how it goes. Okay, so then a little bit of hints. Now, verification for flexible body, very important thing is that when you're moving information or when you're converting information from finite element model to multi-body system dynamics, you can easily make mistakes about units. And one of the easy things to check out that the units is that make sure that you're checking your inertia properties. Just check like how much the body weighs in your finite element model and in your multi-body system dynamics model. And if there's any changes, that's when you need to figure out where the change is actually coming from. You can also compare their natural frequencies using these free modes. You can conduct an eigenvalue analysis in your finite element model, and then you can compare that against the ones that are the modes you're using in your multi-body system dynamics models. And visually, you can compare how is the deformation look like. So those are the three tips, verification tips. Okay, with that, I see that I've been a little bit slow today, and there's an awful lot of things to discuss because this one here, contact modeling, that's a kind of long story and takes way more than 45 minutes, and still I need to discuss shortly about this mass invariance before we're ready to move on to contact modeling. So any questions, any comments so far? Mass invariance. I guess not. Again, I see that once we back in this face-to-face teaching, this kind of communication, like any comments, any doubts, will be so much easier to conduct face-to-face than it is here in a YouTube. And again, even if you are not able to come to lecture room in person, that's okay because the lectures will be streamed, even though that they are conducted in a lecture room. Okay, now mass invariance. Now, what's the story about the mass invariance? And this is a long story, like I said, but I'm gonna cut the corners in this long story and I'm gonna focus on the real deal. What really is important in this mass invariance? But like I say, uh, when you're describing flexible bodies using the floating frame reference formulation, the kinematics is as it is shown here. So you have this R that is describing the large reference translation of this reference coordinate system. You have the rotation matrix that is describing large reference rotations of this reference coordinate system. And then you have vector U bar 0, which is describing particle location on its undeformed configuration. And then you have this deformation. And the deformation, like we concluded earlier, can be expressed by using these modes and corresponding modal coordinates. That's where it goes. Now, these modes and modal coordinates, they're coming from the finite element modeling. Now, this one here, and this one here, and this one here too are like the true components of finite, the multi-body system dynamics. So they can be considered as a multi-body system dynamics, whereas this one here is a finite element method. And like like the system is described here, they are fully coupled. So there's no decoupling between these two approaches. So there's completely multi-body system dynamics plus finite element modeling. There are some cases that you don't need to have this full coupling, but you can use a partial coupling. So something that they are kind of combined, but not fully combined. And this is where the mass invariance comes into play. And you can play with this coupling. How strong is this coupling by modifying the mass invariance? So that's why these mass invariants are kind of important. So now what follows is that we should, to be able to explain the story from beginning to all the way to end, we should take a look at the very heavy details of the equation of motion. And I'm about to do so, but this will be a good time for you to go and take refill your coffee cup, relax a bit, because I'm not going to plan, there is no plan whatsoever to ask about these details. How did you derive the mass invariance? I'm not planning to ask that. But again, I would like to emphasize that what's the big picture and why these mass invariants are actually important. But now, take a look at something else if you are not a big fan of the theory, because what will come will be the hardest so far in your life. I can guarantee you that, because this is way more difficult than any of the stuff we discussed in a simulation of a mechatronic machine. But again, like I promised, I can only use 5 minutes to describe this to you. All right, so here it is. So here is the kinematics of the floating frame reference formulation. So we have here large reference translation, large reference rotation, and then the finite element method here, to put it in a short, or cutting the corners. Now, how is it we're describing this flexibility will be based on the number of modes. These modes will be associated with these modal coordinates, and this time we're selecting that there's NB number of modal coordinates. Okay, so not big surprises. Vector of tenorize coordinates will be modified. And you see how seriously this selection of kinematics is affecting us, because every single step needs to be redone here. So we cannot rely on anything what we discussed earlier, but we need to do everything again, even including the vector of tenorize coordinates. So even that is no longer the same that it was, because we have more unknowns. Now, initially, when you're dealing with the rigid body dynamics, you have this translation and rotation, tenorize coordinates as your unknowns. But now because of the flexibility, the model coordinates are added to the vector of generalized coordinates. And this is how finally the vector of generalized coordinates look like. Okay, you know that this is what we need when we mapping forces from global coordinates to generalized coordinates. And you can imagine already that this mapping gonna be a nightmare because we have this lengthy vector as a generalized coordinates. But one thing at a time. So first thing we need to do is that we need to express velocity. So we need to differentiate this equation. Well, I'm not going to write this equation, but this equation maybe would be this equation here. We need to differentiate once with respect to time. And this is how it looks now. And now, earlier, we were able to say that this third component here, vector u bar, that was equal to 0 because there were no deformation in the body. In this case, we cannot do that. So u bar dot is not going to be equal to 0. Why? Because remember, u bar dot consists of u bar 0 dot u bar f dot. This one here is 0, but this one is not 0. So it's going to change your life radically, very significantly. Okay, so this is how it is put it in a writing. So this is how the vector u bar is. And once you do the mathematical manipulations and once you express the velocity in terms of generalized coordinates, this is how it looks like. Now, take a look here. So this is a vector of generalized coordinates, and these are the components needed to do this expression. All right. Now, shortly, this is called as a L. Now, here's what I'm going to speed up. Now, this is how acceleration looked like. And now the acceleration this time, now this is important. This time is no longer consisting of three components. Remember, in the rigid bodies, there was a translational acceleration, there was this normal acceleration and tangential acceleration. Now we got more acceleration components. So we finally got this Coriolis acceleration because now the particle can move in a rotating disk. And then we have acceleration just due to the pure deformation. Okay. Now we can substitute this acceleration description to our expression of inertia forces, and this is it's going to be a big mess, so it's look awful, but don't get upset about that. So it's look even more awful. So it's going to be mass matrix. That this is how you can describe the mass matrix. This is how the quadratic velocity vector looking this time. And once you keep on manipulating things, finally your mass matrix started to look like this. And now the mass matrix is the one that consists of six different components. Where is my camera? 6 different components. This is where the mass invariants are actually called. So now what you can do in your mass matrix is that you can introduce how much you are coupling your description of deformation and your reference motion. And that can be accomplished something that is called mass invariance. And these mass invariants are simply the components you use to compute these 6 submatrices in your mass matrix. That's what they are. And now they have a different name. So there is a total of 9 mass invariants, which like the mention here, well, like the title implies, those are the components that remains constant during the simulation. But still you can either ignore it or take those into account. And what they means to you, it means like how well you coupling finite element and your multi-body system dynamics. This is how you can, how they can be computed. And this is a screenshot from a commercial software, Adams. Look at the numbers. So the numbers are 1 to 9. The same numbers are shown here. And this is where the user can actually start to playing with this, how well they are combined. And as you can see here, this is where the user can put these mass invariants to be active or inactive. What it means? It means that you can combine the finite element model and multi-body system dynamics fully, partially, or in a way that you tailoring by yourself. My record, my recommendation to you is always use a fully coupling because no one really knows well what it means to use this partial coupling. So why is that there is this option of partial coupling? Because the partial coupling increase computational efficiency very significantly. So you can make the much faster computation, but you will also lose a little bit of accuracy. How much? No one really knows that so well. So that's why this you're kind of stepping the thin ice because you really don't know is it able to hold you or not. So my recommendation again, keep them all fully coupled, then face the consequences, which is just a little bit of a slower computer, but that's what it is. Okay, so now here comes my third in-class quiz of the day. Role of mass invariance. And I've been repeating this, I don't know how many times, but many times today. So the role of the mass invariance is that it allows to describe structural damping, allows to describe external applied forces, couples stiffness and damping, couples finite element model and multi-body system dynamics. Now, how is the success rate this time? I'm thinking yes, 100. That's my thinking. 100%. Okay. But now, if any other comments, questions, let me know. Okay. And while you are, let me see, I have 0. I got the first answer already. Now, while you're thinking that, so let me open this because I'm a little bit in a hurry. I have less than a half an hour time to go. And there will be no way to complete this topic of contact modeling within this time frame. But anyways, I will get started and I will open the topic of contact modeling. And then I will continue, don't know when actually. This is a little bit inconvenient because the next week I will be around, but I'm not the one that is delivering the lecture, but it's going to be Arend instead. Week after that, it's going to be Ilkka, and then Adam. So it takes, what is it? 4 weeks before we're able to close the case of contact modeling. Sorry about this inconvenience. So 80% again is a voting action. You do that, then you do the voting, and let me take a look at the content modeling. This is these screenshots are from the game that is very old game. I think this game is called Flat Out, and it shows a little bit about how is a contact modeling. Contact modeling in games and in multi-body system dynamics, there's quite a bit of similarities. Actually, many of the techniques that are used in a games are now used in multi-body system dynamics. So it can be considered that game contact modeling in certain perspective is even more advanced than the ones that are used in a multi-body system dynamics. So how it goes, how is it we can describe the contacts? How is it we can describe the collisions situation like you see here? So there's a TV screen or something that is placed top of the car, and then there's another car that is dropping down here. How this can be described mathematically. That's what we're gonna discuss next. First thing, the contact modeling consists of two different steps. And these two different steps are contact detection and contact event modeling. Contact detection means that we have to figure out where there is a possible contact. And this is something that typically is computationally very demanding. But there have to be some kind of clever algorithm for that. And why is that? Because there is so many different possibilities for contact. You cannot just simply model them by using if-then approaches, because you do that, then your code gonna be a big mess. Think about the rally game or vehicle modeling in general, because in a vehicle modeling, if this is a vehicle here, let's say that. Sorry about that, because it was my phone ringing. So this is a vehicle here. Let's say that is a rally car, and the rally car goes around the road, which is, let's say, 10 kilometers in a length. And it's possible that the rally car can hit the trees that are along the road and along this path here. So there's a possibility that this part here can contact the tree that is located here, but it can be also contact the tree that is located here, and many, many others. So there's a lot of possibilities how the contact can take place. So we have to have an algorithm, some kind, that is computing the contact detection, figuring out whether or not there's a possibility of contact. And if it is yes, then we're going to move on to the next step, which is a contact modeling itself. But typically, this contact detection is harder. Well, okay, let me rephrase. I don't know which one is harder. The both are challenging. But typically, people are focusing on the contact event modeling. And don't forget about the contact detection, because the contact detection is extremely, extremely important. Now, with that, let me go back to our in-class quiz. This one here. You don't see it yet, but this is it. And the voting is 80, 90, 93, 97. Okay, and the correct answer is 92. This was the highest so far. I think this was definitely highest so far, but not 100%. Oh, we got the 93s. Oh, we got two 93s. Nice. So we got a lot of people that should definitely do the lottery. Do the lottery. So you need to be very good to guessing the numbers. Okay. So what is? Let me take this off. No, this one. This one here. Like I said, the role of the mass invariance is that it couples finite element modeling and multi-body system dynamics. It doesn't really couple the stiffness and damping, so not really to do with that. It doesn't really allow to describe externally applied forces. It's not more really allowing to describe the structural damping, but coupling. That's what it's doing. Okay, so with that, let me go back to now where? Here. Contact modeling, contact detection, contact event modeling. Okay, so let's get started from the contact detection. The contact detection that is it's like pretty much always used in one way or another. There's different variants, but very, very often uses this method that is called bounding box method. And the bounding box method is a method that you are using different level of objects. And these levels are typically root level, branch level, and leaf level. And what are these levels? So they're like, roughly speaking, bigger to smaller objects. Because if going back to this rally car, it's going to be very, very hard to describe whether or not the single graphical detail, let's locate it in this corner of the car, whether or not that is contacting the tree that is located up here. That's going to be hard to do. So what we can do then is that we can put a very big box around this vehicle here. All right. And then we can put the boxes around this rally road like this. This is where the possible collisions could take place, like this, that many. And then we can use a clever algorithms that is just monitoring whether or not these boxes are colliding. And this is this root level boxes. Now, if the boxes are colliding, then you know, okay, we're getting close to the possibility of contact. And then you're ready to move on to next level, which is this branch level. The branch level still is like a smaller box inside of this bigger box. Let's go back to this rally car. Now it becomes to be a little bit messy, but it could be that the rally car itself consists of 4 boxes. Each of the corner of the box, these are the boxes. So these are the branch level boxes. The branch level boxes, like here is another example. This is a device that is used these containers from harbor to crane. And look what is top of this what is top of this device here is a big box. This box here, which is a root level box. Then there's a smaller boxes, which is like describing this particular detail here. These are the branch level boxes. And another root level box could be entire ship. So it could be this particular device against a ship. And if you see that the root levels are colliding, yes, well, let's move on the branch level. The branch level are colliding, then you can use the drawing object level. So you can look at the drawing primitives, exactly. And if the drawing primitives are colliding, then you know. Here where the collision is taking place, okay, so we definitely need to do something for that. What you can then do for that is that you can make them separated. How? Well, that's contact modeling then. Contact modeling, which we're going to take a look momentarily. All right. Now, how are these different boxes? How are the different technologies in these boxes? Well, we can have a number of different ways we can put the boxes around the object. We can use this oriented bounding boxes. We can use axis aligned bounding boxes. Well, doesn't really matter how you do it, but the concept is still the same. Concept is still the same. So there's a bigger box, the smaller boxes, and the drawing objects. And then finally, you're able to make a prediction of possible contact. All right. Now let's say that, yes, we got the contact. We have the red flag here. So there's a contact between these two bodies here. What is that we can do for that? And now, in case of contact, what usually happens is that there is a local deformation. This is something that happens in the real life. So the bodies cannot really penetrate with respect to each other, but there is a local deformation. To describe that accurately, you should model your bodies as a flexible bodies. And you should look at the local deformation of, let's say, in a sprocket system, you should look at how the teeth are contacting and how is the deformation because of these contacts. You cannot do that in a multi-body system dynamics. So it's not really possible to do this detailed contact description. So what typically is then made is that you're using bodies that are undeformable, rigid bodies. This will be a better way to put it. In a rigid bodies, you can then make them separated using two different approaches. And these two different approaches are called penalty forces, or you can use something that is called cone complementary approaches. Penalty force is, like the title implies, is a force that is forcing these two objects to separate. So if I can see that there is let's say that there is a ball that is coming to the surface here, I can recognize that there is a contact. I'm allowing this ball to penetrate this surface, and now because of the penetration, amount of the penetration, I'm introducing the force between the ball and the surface that will shoot this ball away from this surface. That's what the penalty force is about, shortly speaking. Then there's quite a bit of details related to that, which we're going to take a look at in details momentarily. Another way we can do this is that we can construct here inequality constraint equation. So it could be considered more or less similar way than constraint. So I'm saying that the ball here can do whatever it wants, except it cannot go through this surface. So it can fly anywhere it wants, but it cannot go below this surface here. And this can be expressed mathematically by using inequalities. And you can put these inequalities in a form of constraint. And you know that in a multi-body system dynamics, we can handle the constraint. We can even handle this inequality constraint. And this is where this cone complementary approach comes into play. Now, roughly speaking, let me take a little bit of coffee here. Now, roughly speaking, the penalty force is something that works well if you're dealing with the relatively more small number of bodies. And if you have, let's say, the bodies that are less than 50, less than 100, you can use a penalty force. So it's not going to be a big problem to use it. It still comes with the certain complications, comes with the certain difficulties. But if you have more bodies than that, if you deal with 1,000 bodies, 100,000 bodies, 10 million bodies, then the only way to go would be this cone complementary approach and these inequalities. And that's actually takes us the method that is no longer necessary called multi-body system dynamics, but many-body system dynamics. And many-body system dynamics is, well, system that consists of many bodies. And usually, so it's like, let's say more than 100,000 bodies, then it can be considered as a many-body system. Where is it you need 100,000 bodies? Well, you may need it when you're modeling the travel. So if you wanted to model the vehicle, off-road vehicle, moving in off-road surface, and you wanted to make the ground to be something that is deformable, the one way to do that is by using a lot of bodies. So it could be like sand particles, not as small as a sand particles, but close to it. That could be the way to describe this deformable ground. This is where the many body dynamics comes into play. But let's get started from these penalty forces. Now, penalty forces is all about allowing two geometries to overlap, to penetrate. So this is what is you have to do. So even though that you're dealing with rigid bodies, you're kind of assuming that there is a kind of local deformation, indentation, if you may, because of this local deformation, which you cannot describe because you're dealing with the rigid bodies, it takes in a form of penetration. Because of penetration, I can compute the force that is separating these two objects away from each other. And it's kind of simple. So it goes in such the way that you have here a force that is a function of the penetration. The penetration here is considered to be x here. So let me make a drawing here. So it's a ball surface. How much they're penetrating is measured by x. Then there is going to be a stiffness that is one way or another associated to material properties of the surface and the ball. Okay, not necessary if you deal with the stiffness material, you may not be able to use elastic coefficients because those can introduce too heavy penalty forces. And then you have here exponent, which is kind of the way that these penalty forces comes into play. Typically, the exponent is not 1, even though that is like obvious solution. And why is not considered to be 1 is that then the system behaves like that is shown in this figure here. So what's the problem in this figure? The problem is this, that when you're traveling, from when the ball is traveling, well, let me put the here, from ball is traveling here, getting close at the surface, and finally it hits the surface. What happens when it is hitting the surface is this discontinuity. So you're moving from 0 force to the curve that is increasing linearly. You see that here there's this discontinuity that in some cases can cause quite a bit of headache. So what you could do then instead is that you can smooth this discontinuity by selecting the power number, this n, to be other than 1. So it could be if it is 2, you can see that this is increasing progressively, which is not exactly what you can see in a real life, but this is computationally more pleasant. Or you can use a 1.4, 1.5, something like that. So this is a typical scenario you can see in a real life, because then things are smooth. So when you're moving here and you're moving to penetration, there is no violent discontinuity that takes into place, but everything is smooth. All right. So that's basically what this penalty force is about. So I'm going to skip this example here, but I'm going to show you another example. This is something that is a bearing modeling. So the bearing modeling where the ball bearing is modeled by using this kind of penalty forces. So basically, there's a like inner ring here, outer ring, and then the balls. And the balls are not really the balls, but geometrical representation, which is not the real representation. So this coming without inertia. So we can compute how much there is a penetration, and based on the penetration, we can compute how much is a penalty force associated with each one of these balls. And this is how you can introduce a bearing model. So the bearing model that can account um, on idealities like oval inner ring. One, you can make the one ball off. You can introduce a fatigue crack or whatever you want for this kind of a model. But how it goes. So let me shortly introduce you the details. It's all about this equation. This equation here, which is exactly like we looked at in one couple slides back. This one here. So no difference. So one is more elegant to expression than another, but the basic concept is still the same. And now I have here stiffness, which I can compute based on the material properties. And then I have here this penetration. And the n here, look at n in this case seems to be 1.5. And I can do that for each one of the balls. I can look at how they are behaving. And this is how I can make the bearing modeling. And there was even, this study was made already. Well, this was actually at the time or when Jussi Sopanen was a doctoral student. And this was close to 20 years ago. Close to 20 years ago. Part of the Jussi's doctoral dissertation was this bearing modeling. And the bearing modeling at the time was made in Adams software. And there was even a user interface created for this Adams software such that it helps you to create these bearing models very rapidly. So you basically just introduce geometrical properties of the bearing you wanted to deal with, like outside bearing outside diameter, bore diameter, and so on and so forth, bearing type, a lot of different information. And what happens automatically was the bearing model itself. And then you were able to introduce some defaults to your bearing model. So let me see how it works. So this is a bearing model. You see, by the way, that the reaction force here is fluctuating all the time. This is simply because these balls will carry this system differently. So the force, when you look at the inner ring, outer ring, and when the poles are in this direction, force what is traveling here have to go through this one and this one. And it's going to be different supporting force when comparing that the force is traveling directly here. So this scenario is different. This one here is different than this one. And that's why in this animation, this reaction forces is fluctuating all the time. You see that is well, I don't see the numbers so well, but it's you see that it's not the constant value, but it's changing, and that's because of the how is ball positions. And you can introduce some well, different kind of scenarios. This I don't remember what was this scenario. You can introduce also some non-idealities. Outer ring could be triangular shade. You can have a fatigue crack here. All this kind of stuff. But all these using simple penalty force approach. Simple penalty force approach. Here, there's no, by the way, no need to use any kind of contact detection approach because here the contacts are, and the number of contacts is so limited, so there's no need to do that. So, not need to do that. Okay, what's the problem in a penalty force? So, what's the observation regarding the penalty forces? Simple to use because it's just the one external force, so it's simple like that. There's a big problem associated with the method. And the big problem is that it is typically very sensitive to integration settings. And typically it requires that the computational time steps have to be small enough. And that's simply because it's based on the penetration. And the force is a function of the penetration. And typically there's no upper limit how much the penalty force can be. All right. So what it means. So let's take a look at this ball and the surface again. Ball and the surface again. And now it could be the scenario such that we are computing this system by using a very high time step. So delta t is very high. So in a one time step, the ball is located here. In a second time step, the ball is located here. And in a third time step, the ball is located here. And look at that amount of penetration here. X is huge. And now if this is a steel material and there's a penetration this much, you can imagine that the penalty force that is pushing this ball away from the surface will be huge. It's going to be very large. And because of that very large force, the system is not behaving realistically, but very unrealistically. That's a big problem. So typically you need to use very small time step to avoid the fact that there is no high penetration. Or alternatively, what you can do is that you can play with this stiffness parameter. The stiffness parameter could be kind of low, but that sometimes allows or takes you to the situation that is not realistic. So it's something that, it can be high penetration, something that you can even visually observe the penetration, something that in real life will not take place. But because of this penetration, you need to be careful with the integration settings. Very often used method. Most often used, I would say. Okay, now my last in-class quiz of the day. I think the ID, by the way, is not 4, but, not 3, but 4. And I'm asking this. Contact force can be described using penalty forces. Drawback associated with this method is damping is difficult to describe, multiple contacts are difficult to describe, method is sensitive to integration settings. So this is my last one. Which one is correct? And once I'm done with this, I'm going to close just checking. Okay. There is a question. Can the time step to be changed when the object is getting closer to contact? Yes, there is a variable there is this time integration algorithms that are based on the variables time step. So it's possible that when you see that something goes wrong or something happens, then you can change your time integration steps. But typically the problem is that so if you get, if I go back here, this one here, if I go back here, you're using very high time step, even though that you have this opportunity of changing your time step. If you end up to be in a situation like this much penetration, it's like almost too late to correct anything at all. So this is going to be something that you can tune the system, but the system cannot see that there's a contact about to come. So that's why it's kind of colliding too heavily. He's doing the too much penetration. Later, he started to correct it, but it's already too late to do so. But again, if it happens to be such that, the first penetration will be this much, then this variables time step integration scheme will automatically recognize, hey, wait a minute, there's something weird happening here, so let me reduce the time step. So it helps in this case. But if there's like too heavy penetration, I don't think that it can save the severe situation like this. Okay, so with that, now let me take myself here. 11 answers, and I think this is it. So because it's 9:45, so it's a time to close today's lecture. So success rate 73. So we still have a little bit of to go before we're in 100%. But I definitely would like to see that to happen. Didn't happen today. Hopefully, well, I don't know about Aren. I don't know if he's going to use in-class quizzes. I guess he will. And I will be so disappointed if you're going to score 100% when Aren is delivering a lecture, and never when I'm doing so. But anyways, again, stay tuned. I will email you instructions. But I'm again thinking that uh, lecture will be face to face. I need to double check that from the LUT administration. If not, we meet here in my YouTube channel. So it was a well, that's about all this lecture today. You guys take it easy and